Welcome to Cybersecurity Analytics at the School of Computing, Universiti Utara Malaysia. I am Dr. Ala Jabar Al-Maliki, and today's lecture focuses on the foundational step of all security operations, data preparation. This is what modern network traffic looks like at the collection point. It is a continuous, unstructured cascade of raw hexadecimal codes and packet data. In this state, these logs are computationally chaotic. They offer no immediate diagnostic value to security analysts and are mathematically useless to machine learning algorithms. The primary challenge in cybersecurity analytics is not the collection of data. The challenge is the signal-to-noise ratio, isolating actual microscopic threat indicators from the overwhelming background noise of normal system operations. Before any threat detection model or machine learning application can function, this raw data requires rigorous, systematic preparation. If we fail to engineer this data structurally, we guarantee the failure of the entire analytics pipeline. Then, the algorithms will process noise and return false conclusions. We begin with data mining. This is the computational process required to extract actionable, operational knowledge from massive datasets. To function at the scale of millions of packets per minute, this process relies heavily on advanced statistical and mathematical techniques. The first objective of mining cybersecurity data is detecting anomalies. The system establishes a baseline to identify deviations, such as unusual login times or irregular geolocations. The second objective is identifying specific attack patterns. In this server log interface, we see dozens of identical failed login attempts originating from a single IP address. The algorithm clusters these events, successfully flagging a brute force attack. By identifying these historical patterns, including specific malware signatures, the system gains the ability to predict potential threats before they fully execute. Data mining is an active, algorithmic extraction. It is the exact mechanism that turns raw logs into definitive intelligence. To make data mining efficient, we must apply feature selection. This is the process of choosing only the relevant variables from a dataset for our models to analyze. Datasets inherently possess dimensionality. When we feed a model too many variables, the computational complexity skyrockets, overwhelming our processing capabilities. Consider this data matrix containing over 50 distinct variables. By applying feature selection, a scanning algorithm evaluates every column to eliminate redundant or useless information. A variable like packet size is vital for detecting anomalies. However, arbitrary routing tags or an indicator like packet color provide no diagnostic value and are deleted. We retain only the essential network features: source IP address, destination port, packet size, time interval, and protocol type. These lock into a new compact table. This selective reduction directly decreases processing time while simultaneously increasing the ultimate accuracy of the analytical model. Feature selection acts as the analytical bottleneck. A machine learning model is only as accurate as the specific mathematical variables chosen to train it. Choosing these variables is rarely done manually. We rely on three specific algorithmic methods to execute feature selection. Filter methods rely on statistical correlation. They evaluate and filter out weak features before the predictive model is even trained. Wrapper methods use the predictive model itself. They test multiple different combinations of features, evaluating the performance of each to find the optimal subset. Embedded methods perform feature selection automatically. The process is built directly into the machine learning algorithm's internal learning cycle. Regardless of the specific method applied, the end goal remains identical: reducing an unwieldy dataset down to its most potent, predictive mathematical core. Even after selecting the right features, the data is still raw. Data pre-processing is the multi-step pipeline required to format that raw data perfectly for analysis. Step 1 is data cleaning. Analytical algorithms are strictly logical. They will fail catastrophically if they encounter structural inconsistencies in the input. This means the system must systematically remove duplicate records and correct any formatting errors across millions of rows. A critical cleaning task is handling missing data. Here, a row contains a null login timestamp. Because the system determines this value cannot be accurately interpolated, it deletes the entire record to prevent an algorithmic error downstream. Step 2 is noise reduction. Analysts must differentiate between actual malicious anomalies and random benign system variants. For example, random traffic spikes occur nitrally during peak business hours. These variations are noise, completely unrelated to cyber attacks, and must be filtered out. Cleaning and noise reduction prevent false positives. They ensure the machine learning model reacts exclusively to genuine threat indicators, rather than data errors or standard operational variants. Step 3 is data transformation. We operate on a strict computational axiom. Algorithms calculate numbers. They do not read text. We must convert categorical text data into numerical integers. In this protocol column, a compiler scans the text, replacing every instance of TCP with the number 1 and every instance of UDP with the number 2. Step 4 is data integration. Effective security analytics cannot rely on a single isolated data source. We must merge distinct data silos into a singular schema. This typically involves combining firewall logs, intrusion detection system logs, and internal server logs to create a complete operational picture. Step 5 is data reduction. Even with modern hardware, processing tens of millions of integrated data points in real time hits physical limits. We utilize statistical sampling to shrink the total dataset size. Done correctly, this reduction preserves the exact underlying informational value while requiring a fraction of the compute power. Through transformation, integration, and reduction, we successfully convert chaotic, multi-source text logs into a single, optimized numerical matrix that is finally ready for advanced analytics. This pristine, pre-processed data is what actually activates real-world defense mechanisms. We can see this applied across 3 standard security interfaces. First, an intrusion detection system relies on normalized values and precisely selected features, like packet size and arrival time, to trigger a valid attack alert without overwhelming the operator with false flags. Second, phishing detection models utilize data transformation. They convert suspicious URL lengths and text-based keywords into the exact numerical features required to automatically quarantine malicious emails. Third, security information and event management systems, like Splunk, depend entirely on continuous log integration and pre-processing to correlate events and detect multi-stage threats in real time. These highly sophisticated systems are completely dependent on the unglamorous foundational work of data preparation. To summarize the core mechanics, data mining extracts operational knowledge, feature selection strips away complexity, and pre-processing guarantees the mathematical usability of the logs. Applying complex machine learning models directly to raw, unprepared data will always result in analytical failure. The math cannot correct for poor input. High-quality data engineering remains the absolute baseline for high-quality cybersecurity. Thank you for attending this session for the Universiti Utara Malaysia School of Computing.